children. So I don't have any technological aids, so I'm just going to briefly introduce, so I don't have to shout too long at you without the mic. John, who's giving us this lecture today on Argus 400 and so on, it's been very well publicised. I have to say it's one of the best intros. It's very comprehensive. He's also well known to many of us in this group, so he doesn't really need a big introduction from me. He said that he's quite happy to take questions as you go along, but bear in mind the audio stuff. If you want to hold it to the end, it makes it easier for people with the tape when it gets put up on the web. So just bear that in mind, please. So really, John, welcome. He's described to me a really ubiquitous career from inventor, designer, right through to a very capable marketeer. So I think that's fantastic. And really look forward to what he's got to say. So no more ado, over to you.
Right, can everyone hear me? Yeah. Right. Basically, I've been in this business a long time. This is the outline of what I'm going to be talking about. It's also basically the first 6 or 7 years of my working career because I started at Ferranti. So I'll go through my role, what Ferranti were doing with process control, which is a rather unique branch of computing. There may have some differences that maybe should be obvious, but I will make sure that everyone's aware of them anyway. Ferranti, in terms of process control, had a range of computers available, and I'll go through those briefly. We also developed at Ferranti our own integrated circuits, which were one of the reasons for the computer that I was involved heavily with. So we'll talk about the evolution of that and the modular approach to the I/O infrastructure, which was necessary to reduce costs and increase flexibility. And provided this time, I'll deal with some of the challenges that Ferranti as a company and I met on the way. Some personal challenges which were quite fun. But going right back to the beginning, I went on a school trip, I think it was certainly a trip to Manchester University. Can't remember the date exactly, it was either 58 or 59, thereabouts. The Mercury computer, which is pictured there, had just been delivered and switched on, which Simon at the front knows much more about than I do. And that's the machine, as I remember it, going as a schoolboy, looking at this system. And that convinced me that I wanted to go into computing as a career. So it set the whole career in stone. I chose Manchester University and they accepted me as a university to go to. Electrical engineering was the discipline that did computing at that time. I think the only other viable alternative would have been Cambridge, and for that I would have had to learn Latin to get into Cambridge. Also, I'm an engineer, not a mathematician, and I believe the Cambridge University courses were more based by the maths department than the engineering department. So that's why I went to Manchester, and thankfully they accepted me. Just a brief summary of what I did at Ferranti. My very first job, much to my astonishment in many ways, there was an Argus 100 computer which was based on germanium transistors, and I was told my first job was to convert this into integrated circuits, make whatever changes you feel are necessary or you feel like doing as you go away. That's quite a responsibility to be entrusted as a 20-year-old graduate starting his very first job. But I also contributed later to the standardisation of the I/O bus, and I was involved, as it says there, in many of the peripherals. This is later, from 5 or 6 years, I left at the age of 69. So those are the things that I did. And there's also some very interesting things about analog process control, process controls which has analog inputs, so you get involved in that field as well. So when I joined in '63, this is where Ferranti Wythenshawe was. At the time, ICT was being formed by Ferranti's commercial side, and that was a completely separate company from the part that I was working from. Ferranti Wythenshawe had virtually nothing to do with the West Gorton side of the business, although there were obviously relationships that had been set up by other people that I was not particularly part of. The Argus computer had been designed originally to launch the Bloodhound ground-to-air missile. And the computer was designed to actually link to the radars, set the targets, and fire the missile. Ferranti had decided that he wanted to diversify into process control. And there was a system installed at ICI Fleetwood, Soda Ash plant, which was a very early prototype of process control computing. It was an experiment both for Ferranti and for ICI to see how this worked. That, I believe, was installed around about 1962, but I can't confirm those dates exactly. What I can confirm is there's one being installed at West Thurrock Power Station, because as part of my induction to Ferranti's, I spent 2 weeks on site assisting on the commissioning of that machine. And that was an interesting experience in health and safety. One of the memorable things is we were on the 40-foot level and the turbine halls were down there, with a big round with equipment on it. There was a man belting something with a 14-pound sledgehammer. The head flew off and went all the way down to the 40-foot level, down to the ground floor. He didn't say a thing. He didn't shout down, "Watch out below!" Makes you wonder how much a hard hat would have actually survived a 14-pound sledgehammer. Anyway, that's a digression. They had decided that the Argus 200 was too expensive and not flexible enough for process control. Programming for the Argus 200 was done either with a pair of tweezers or with this little rubber ring put over the ferrite pegs. There was a pegboard store. And 64 words were about the size of an A3 sheet of paper. And I think it was 64 words took a full 19-inch rack. So not very flexible. It was really, really It did have a core store, a whole kiloword of it. And the words, I think, were 12 bits. So not a massive amount of storage. So an Argus 100 computer, that's when they renamed the Argus 2. The original Argus was a 200, was renamed later. The Argus 100 was slower, but it was a 24-bit machine, used core store, and first two machines were being commissioned on the factory floor when I was there. One was for Jodrell Bank to control the Mark II telescope, and one was for Steele, Peach and Tozer, which is making steel in arc furnaces. I actually briefly worked on that machine again as part of my induction. One of the boards had to be fitted horizontally and you needed scope probes to just check it was all working, which was lying on the floor a bit like repairing a car. So that's my early memories of Ferranti. A decision had been made when I joined to develop a new computer, going to be called the Argus 400. And this is a proving ground because they wanted to move into these newfangled integrated circuits which were just emerging from the research laboratories. We had a Fairchild research kit in the lab when I went there. I think that was resistor transistor logic. I saw it but never actually used it. But that was there as a kit. Micronaut 2, and I'll come on to that later on as why it's called Micronaut 2, was being developed, and the Argus 400 was the proving ground to prove that these integrated circuits could actually do real work. And at the same time, they realised that the Argus 100 was probably a bit slow. Clock cycle was 500 kilohertz. The add times were the order of 72 microseconds, I think it was. The multiply time was 1.8 milliseconds. Sounds terribly slow for these days, doesn't it? Anyway, the Argus 300 as a parallel computer was actually being designed as well. That's where it all started. That's just a brief introduction of the family tree. The Argus 100 was derived from the Argus 200. The Argus originally, I believe, was derived from the Pegasus instruction set. It had, I think, 64 instructions. The Argus 100 had 32 instructions. And the I/O address space with the typical machine was 4,096 words of 24 bits, 12 kilobytes. And you could have 3 times that much memory. That was the maximum it would take. The Argus 300 was derived from the Argus 100 and it had to run the same instruction set. But there were some additional instructions added. The Argus 350, which came later, I believe could split the word into 2 and actually do 12-bit arithmetic to speed things up for multiplies for flight simulation. Now the Argus 400, which is where I started, was supposed to be based directly on the Argus 100. All the data is held in core store, the IO address space was the same as the Argus 100, and I made some minor tweaks to the instruction set to simplify the logic. These were compatible tweaks, and they were followed on with the other machines as well. The Argus 500 was based on the 300, but was also done with integrated circuits, and that had some significant enhancements to the instruction set. Don't ask me questions on that particular part of the instruction set because I don't know the answer. We did that in 1 microsecond and 2 microsecond store versions, so with 1 microsecond Argus 500 is getting to quite a fast machine. As an aside, which is why they're in different colours, later on we did an Argus 600, which was an 8-bit machine intended as a remote batch terminal. That was a low-cost machine, but the important thing is it could access some of the same I/O devices. The I/O stuff was compatible. And the Argus 700, which came later, was a 16-bit architecture, was what Ferranti were just developing when I left at the end of '69, and that became the workhorse for the rest of Ferranti's life, and was retrofitted into some of the Bloodhound stuff. There was one up in the Midlands that worked on a trip there recently, which showed one of the 700s. That was still using some of the I/O equipment I designed in the 1960s. That's the background. So the Argus 400 is where I'm concentrating on. So there's the integrated circuit design. The integrated circuits, we decided there was nothing in the market that actually existed that would suit what we were trying to do. So, Ferranti being Ferranti, we'll design those and make them in-house. The logic design was based on the Argus 100, but with 1 or 2 minor changes, which I did, we'll perhaps talk about later. We had to do the mechanical design. Nobody knew how to lay this thing out into a computer. The target was an aircraft case, an ATR case, which is about that size, the whole computer. About the size of a large shoebox. And I've got some pictures of this in a minute. So 3 to 5 inch sections, I'm not sure the photograph of that. And there's an I/O section with 18 printed circuit cards. And they decided the integrated circuit would use TO5 cans, metal cans. The rationale for that was they were making it partially for military use. You could fly these in an aircraft was the intention. So they're looking for the ruggedness of a metal can and potentially the reliability. We only later changed to the dual alignment pattern which Texas used for their 74 series. And the CPU was 18 of these cards with 39 cans on each. The cards were about that long and that deep. 3 rows of 13 cans on them. You can have 1 to 3 core store modules. There's photographs of this in there. They're PCB multi-layer printed circuit cards. These were a novelty to the drawing office. They'd never done multi-layer boards before. And we needed a modular interface to the I/O architecture. Integrated circuits. Ferranti's liked to do things in-house. They were that sort of company. I think it came from their original birth in the late 1800s when the Ferranti were doing this sort of thing. They made everything electrical, and Ferranti's Withenshaw still wanted to do the same thing. Prior to July '63, that date's important because that's when I joined Ferranti. It created a diode transistor logic range called the Micronol 1, and I've got some equivalent circuits for that in a minute. It was a rather strange and unconventional design which had poor noise immunity. During 1963, they decided to actually design a different type of circuit, which is why it's called Micronol 2 rather than Micronol 1. And that was being prototyped when I joined Ferranti. There's the equivalent circuits of Micronol 1, which, as you can see, the base is stuck out on a long wire which trails all over the computer, so it's not very good for noise immunity. And the fan-out is controlled by separate diodes on each of the outputs. Well, it's strange architecture. Micronol 2 is still DTO, but much more conventional. And I think those register numbers are correct from memory. But do bear in mind that I'm now talking about memory from 55 years ago, and my memory might be fallible, but I'm pretty confident that those are correct. The other thing we had to decide in those days, 1963, is what is logic 1? The Ferranti Argus 100 range used germanium transistors with negative logic, the PNP transistors. So 0 volts to minus 6 volts. Ferranti's chose 0 volts to be a logic 1 and minus 6 to be a logic 0. The rationale there is if you put a transistor which closes a switch and you put a light on it, and the light lights up, that's a logic 1, isn't it? That was the rationale behind it. When you come to changing things over to NPN transistors, what do you do about logic 1? Do you shift the range up that way, or do you flip it? Francis decided to make logic 1 0 volts, and logic 0 5 volts, 4.5 volts, sorry. And that's illogical. Unfortunately, the rest of the world, when they produced TTL, decided the opposite way around. So it meant that the Texas 74 series NAND gate and the equivalent micro-NOR logic were identical. And it doesn't half cause problems when you're a logic designer trying to actually follow a printed circuit diagram. Which the hell is logic NOR? I had to do that calculation. I don't know what Ferranti's did after I left in '69, but they were still using this convention when I left. So there's a bit of comparison there between the 74 series, which were eventually produced later, and one of the things being TTL, the thing we used to be able to do is connect collectors together as a wide OR. You can't do that with a total pole TTL circuit. Anyway, that's the general sort of characteristics of the thing. Metal, 8-link TO5 cams. We did repackage all the micro-NOR stuff into 14-link dual-link line formats, so they're incompatible with the 74 series. A good noise immunity, which is far better than TTL, of about 0.8 of a volt or better. We had 7 nanoseconds propagation delay with a maximum of 10 nanoseconds. I think TTL was 10 nanoseconds from memory, so it was faster. I don't know what the fan out of the TTL is, I can't remember, but the original design was 4 for gates and 3 for bistables. Did the design of the Argus 400, we found that was probably not a good idea, and we increased the fan out, we doubled it. We were making integrated circuits after all, so we could actually tweak the two together. And the chip designer, the guy I knew quite well, this guy called Peter Bagnall, changed the specifications, so we went up to output rate 8 for the gates, which is quite useful, and 6 for bistables. We did a little bit of SSI, small scale integration, when we did the original design, and I'll come on to that in a minute. We also had a power OR gate, which would allow drive a fan out of 25, which was very useful for a 24-bit machine. Allows us to drive all the 24 inputs. Fixed selectors. The temperature range was 0 to 50, but we did have a military version. I know the plus 70 is correct. I can't remember the minus 20, whether that's correct or not. It might have been minus lower than that. We did have a military range as well. I'm not aware of any machines being built with the military range components, but we did have the specs and the ICs were tested against it. The other fun thing was, when Texas Instruments brought out their 74 series, inconveniently they used 5 volts for their VCC rail. We used 4.5. What do we do now? So Peter Bagnall, chip designer, trotted over to the manufacturing plant, took a whole day's production, changed the settings on the test equipment to 5 volts instead of 4.5 volts, ran the whole day's production batch through again. All passed. So we retrospectively changed the voltage spec for all equipment delivered in the field to 5 volts, which I thought was quite interesting. No chips failed. Makes you wonder what the voltage spec really was. This is the small scale integration that I was mentioning. The chip was originally designed to connect JK flip-flops together and select 2 sources. One was the left and one was the right shift, passing data backwards and forwards through a serial shift register. It's a serial machine. One moment of aberration, I suddenly realised that by connecting that back there and having a data set and a reset line, you've got a bistable as a latch. Now the reason why that's important is cost. The JK flip-flop in the early 1960s, and this is an issue to do with integrated circuits and the way that they're made, It depends heavily on the purity of the silicon that you can get to make the integrated circuits on. We were making these on 1-inch slices, which are cut from a crystal grown like that. Ferrantis were unable to get silicon of a very high degree of purity. It was good, very highly pure, but with the design of the flip-flop, together with the purity of the silicon, conspired that we were getting something like about 0.1% yield. JK flip-flops, when I got started work, I was getting paid £17 10 shillings as a graduate engineer, or £884 if you work it all out. The JK flip-flop was £25, right? That's expensive. When I think about it, another benchmark around about this time was a new Ford Anglia, was £450, and a new house was £3,000. This is 1965. Just put some benchmarks on prices. Computers were relatively expensive in those days. So that small-scale integration, that cost about £5 or less. That cost £25. When you've got lots of them in the machine, it can make a significant cost saving. So we used lots of those. Like once I discovered it, that was one of these eureka moments. So comparing it with the 74 series, noisy immunity was significantly better. Propagation delay was faster, but the tolerances were actually much tighter. So when you're designing a complex circuit, you could rely on the propagation delay in the worst case. Ferranti's approach to logic design was designed for worst case. Take every gate on theory at its worst case conditions. If it still works then, you won't have a reliable system. I know that not all companies do that, because the company I left in Georgia said, oh, don't worry about that, just design for normal. I believe the fanouts are comparable, but I can't remember the original 74 series specs. I know the power gate was equivalent, was very forgiving, because I had one board which actually had a circuit fault on it. And the collector was connected directly to the 5-volt rail by accident. And it was about a fortnight before I found where the short was. It was other more priorities. I found it out because I put my finger on the thing and I caused a blister on that chip. That chip worked when I took the short off. It still survived a short for that length of time. The voltage spec, as I've said, was changed to be compatible. You can't do wired OR functions, which we were using very heavily. It was very useful as a way of saving chips. And the Julian 9 versions were designed to be compatible. Now, mechanical design, and again there's some pictures which will make this clearer in a moment. The CPU cards was about that size. It had 2 rows of pins soldered to the card. These were pushed through into a backplane. There was a similar row of pins, and we connected a wire link between the two using wire wrapping. So the cards were all wire wrapped together. So you didn't have to take the cards out very often, but wire wrapping was a very reliable method of joining 2 pins together. Taking one out was very quick. Taking all the wire wraps off the other things wasn't, but somebody else could do that. You just went on with a pair of snips. You had to unwrap one row, you could take them out in about 5 minutes. The chips were reliable, so it didn't matter that much. This was aimed for reliability of operation rather than necessarily ease of maintenance. You shouldn't need to maintain it very much. We had the backplane hinged together, and there's a photograph coming up in a minute which will show this better. And the backplane, when we had these original hinges, which were basically allowed to open, as you open it, you stretch the backplane. And we were unable to find a method of hinging which didn't stretch the backplane. I think we could have made the backplane longer, but I don't know why we never did that. That's something I wasn't involved with. So an alternative hinging arrangement was made, and I've got a photograph which shows that. Now the other thing was that the Argus 400 was intended possibly to be an airborne computer. It was designed to fit into an aircraft case. We did actually quote using an airborne machine. Anybody remember the TSR-2? The TSR-2 had selected my computer, the Argus 400, as being the computer to link the forward-looking radars into the autopilot. So I was quite disappointed when that was cancelled. My whole career would have probably taken a different direction if that had happened, because I got myself down to do the I/O equipment for that. We got Concorde at the same time, and I gave to one of my team the design of the Concorde I/O equipment. He could speak a bit of French and I couldn't, so I picked the TSR-2. It then got cancelled. if that had gone on, I'd have probably stayed at Ferranti a lot longer and everything would have been different. So, the fun thing was, with it being an airborne computer, we designed it to be capable of sustaining vibration. So, being a small machine, we had a big platform about that wide, big loudspeaker coils, part of the environmental testing environment. You could put a whole computer on it. It's supposed to accelerate it up to 10G. It took about 15 seconds or 30 seconds to break every single wire in that enormous machine. Lots of squaring back into all the things, and started to have to redesign all the cartons. They did solve it, but we didn't put those clamps onto the normal commercial version. But that was quite fun to watch that. I also had to debug the same machine. I think we certainly went down to 0 and up to plus 50 degrees, debugging it at that sort of speed. Just a thing like a baby's incubator. It was just an incubator. You could go through the gloves at the side with the scope rods. The scope rods used to mist up and get frost on them when you put them in the sun. There's the pictures I was promising you. This is the original machine, and you can see the hinges. You can see that the flexible circuit is getting tight at that point. That's a different view of the computer. This is a very poor picture, and I've expanded it. It doesn't really show up very well. This is the machine that's in the Museum of Computing in Bletchley Park. And I blew that up too much trying to pick out the hinges. This part here has been replaced by spring steel strips. It's not a hinge, it's a bit flexible, but it serves its purpose of protecting the machine. Apologies for that, I'm going to put this in yesterday and it's not come up very well. These are examples of the cards. You can see from the hands roughly what size they are. And one thing to notice on there is, for people who are hardware designers these days, where's the decoupling capacitors? We didn't need any. There was no decoupling capacitors at all in the Argus 400. The reason is it's DTL, which is kinder than TTL, which tends to switch both things on together and put a fast spike. But the other thing is we use multi-layer boards. And the VCC layer and the earth plate were only about 10th apart. And that provided sufficient high-frequency decoupling capacitors that we didn't need any big ones. And the power supply feeds to the board on here, to the whole computer, was such we didn't need any bulk capacitors either. When we came, there's a more close-up step. No decoupling capacitors. These holes here were all plated through. We did have tracking on that side, and we had tracking on the reverse side, and we had 2 more tracks internal. That's how it describes it. All the layouts of these PCBs, none of this CAD stuff, it was all done manually by the drawing office. Acetate film, which was about that size for each of the boards. Us as engineers, we had to check these with all the tape on them. They had 1 film per layer, and of course we had the 2 inner layers for the power supply, which normally was standard. If you're really desperate, you could actually etch a strip, etch a little hole to put a connector in there, which we had to do a couple of times. The problem with that is that that had very high capacitance, so you could only do a very short thing. Ferranti had never done multi-layer boards before. We used double-sided, and we tried several card formats before we chose the 18 cards of 39 ICs each for the main computer section. And that was the format was specified. So the bottom layer of the sandwich contained solder pads and tracks. An inner layer was fairly close to the layer above with tracks on it. A VCC layer, a 0-volt layer, an upper inner layer, and an outer layer. There's a big gap between there and a big gap between there. And then plating through. So Ferranti had to learn how to bond printed circuits together. It was a whole new technology. How to plate through holes together, which was a new technology. We were very successful in plating through holes together until somebody accidentally knocked the bung out of the plating bath. They had the recipe of the chemicals that they had to put into the plating bath, but they put the chemicals back in again when they refilled it up, and you couldn't get any holes to plate through for about 3 months. We suspect that somebody had dropped some trace elements in there that weren't supposed to be there, like a cigarette end or something like that. Plating through would not work. They had to buy in a process from the States. We've been plating through for 2 years on the stage, successfully. So this was new technology. You can see the difficulties we were going through. Multi-layer printed circuit boards, I believe they used 150-ton pressure to bond the boards together. The shelf life of the epoxies that came in to bond them together was about a week. So it was all quite interesting stock control. I was not involved in any of that, let's not be clear, so if there's any detailed questions I can't answer them. Part of this stage was logic design, but of course you do get aware of all of these things that are going on as well. So the requirements for the Argus 400, user integrated circuits, that was a given. It was the test bed for Micronaut 2. Micronaut 1 had the noise immunity but did exist prior to I joining Ferranti's. I think it was designed by somebody called Maurice Gribble, who's written several books on this sort of area, including one that claims to be the designer of the Argus 400. I can categorically say he was not. Micronaut 2 was being designed by a guy called Peter Bagnall, who comes the hard way through the graduates, through the apprentice school, ONC, HNC, and was still going to night school when he was doing his integrated circuit. A brilliant circuit designer. So the Argus 400 is a test bed for all of these things, proving that it all worked. So I've said most of that already. The target speed of the plot was 4 megahertz, where the Argus 100 used 500 kilohertz. They said if you can make it run at 6 kilohertz, fine, but 4 megahertz is good enough. I achieved 4 megahertz. The annoying thing is that with an extra 2 or 3 years of experience, I could have made it run at 6 megahertz. It was pure inexperience on my part. My first ever logic design. Logic design, I'm afraid, is something that wasn't very thoroughly done at Manchester University at that stage. My very first ever approach to what is logic design was this. I did find I got a flair for it, so I managed to do it fairly easily, but experience shows later on I could have done it better. We had a brand new core store design, and the previous pictures I should have highlighted. Can I go back? This part here is the core store. There's basically 24 planes in there, it's 12 side by side. And these are all of the drivers for it, and the readams are inside that black box there. The one in Bletchley Park is a later version. I say this is the prototype. And that probably is the machine I used doing the labs. Now how do we go back to where it was? So the environmental specs, I've been inconsistent here about my guesses on the negative temperature. I'm certain of the high end, the 70 degrees, but not certain about the other one. The challenge with the temperature is not just the integrated circuits. It's the core store as well, because the core store has got the cores have got Curie points. And if you take the temperature too hot, the data falls out. And we had thermistors inside the core stores, so that the optimum temperature tracked with the optimum voltage and the optimum currents tracked the temperature to increase the range. We certainly achieved 50 degrees for artistic machines at that range. And the Argus 100 had a similar sort of technology. They were designed for industrial process control to be used in computers, rooms, without air conditioning. So they had a wide temperature spec range. I'm not certain of the military spec range. As I say, I'm not aware if any 400s were actually built with those chips. And that was the original design intent. Instruction architecture. It's a 24-bit machine. 14 bits of address, 5 bits of instruction, 3 bits of accumulator, and 2 bits of modifier. Modifiers are just 3 of the accumulators. Accumulator 0 was basically a source of 0, so it did have one specialised use. Accumulator 1 to 3 was also a genuine accumulator, it can also be used as a modifier. And the modifier, the least significant 14 bits of that accumulator were added to the address before the address was applied. So that adds 3.5 microseconds to the instruction. I've got some slides later which go through the cycles about how it actually works inside. We went through serial arithmetic because it was fewer components and seemed leading to a lower cost. It was also a hell of a lot easier for the drawing office to practice laying out multi-layer boards of a machine of this complexity with a serial machine rather than all parallel paths for a parallel machine. The other features of it, we had 8 interrupt lines, so we can interrupt the machine from one of 8 lines, and we could connect any I/O device to one of the interrupt lines. about 8 busy lines which indicate that the machine is busy, although those weren't very often used because we tended to use the most significant bits of data for busy. And the architecture supports direct memory access, or direct store access as it was called in those days. So we can pause the computer if necessary for bulk transfers, like from mag tape or from disk. They came a lot later, but we did actually have tape and disk access in these machines. I'm not going through all of those, but that's the basic instruction set. If anybody's familiar with Pegasus, might tell me what the similarities are. The ones that caused me a problem, where is it gone? That one caused me a technical problem, the swapping of the two instructions, because of the way that the memory actually worked. You normally go memory read, write back, memory read, write back. That instruction to do it, I had to do memory read, memory write, memory write. So it was a rather strange cycle. And this is the Argus 400 instruction set. The Argus 500 put additional functions in here, and it took some more liberties with some of the jump instructions as well. It had more options on things which are otherwise unused. The accumulator is not actually used on some of them, and it packed some things in there. I'll tell you about those in detail. Function 26 was used for I/O, for sending things out to devices. But with the Argus, that was needed for the Argus 100, so you want to send something from the teleprinter, you use function 26. There's a general store operation of sending things out to that, so using function 10, which logically is the same, worked just as well. That's a change I made. That wasn't part of the Argus 100, it's changed. As I said, I took simplifications where they were appropriate. Those are the shift functions. Again, 34 and 35 were radically extended in the Argus 300. Multiply brings another register in place, so we actually can finish up with a 47-bit product out of two 24-bit words. And function 37 is the reverse, it will take a 47-bit value, and produce a result and a remainder. The machine was designed in terms of the only functions where it makes a difference is multiply and divide. It was designed as a binary fraction machine, so you had a binary point immediately after the sign bit. And this causes great consternation until you forget. If you forget this, when you try to multiply two numbers together, because multiplying 2 by 3 will give the answer 12. It's one place shifted to the left. So if you're multiplying two integers together, you've got to remember to divide shift before you've got the answer. Inside the enclosure, that's how it's organised. The CPU you've seen on the photograph. There's a section to the left which controls both what's called interface A, which is the modular interface going out to the I/O plant hardware, and there's a control panel interface that supports both of those. And to the left of that is a core store. Although the pictures don't show it and the flexible printed circuit doesn't show it, there's actually addressing capability for 2 more core stores. I'm not aware of any Argus 400s that were built with additional core stores in that original design. We did relay it out in a different way once the 500 came into use, and then the core stores were just pluggable. There's a control panel which plugs into the control panel interface. It also can address cards in the peripheral bus for doing particularly the vector reader. The console printer tended to sit on the operator's desk, which is why I've shown it here, but the control panel starts off a process of what's called primary tape, then called interfaces through here, which then accesses the tape. It was all highly modular, and that was the big difference from the Argus 100, where every machine was basically designed from logic cards, which were soldered together into card cages, which were then wire wrapped together between the cages, and every machine was hand-wired and potentially different. The CPU was basically designed with the same wiring schedules, but it was all wired. this is basically the registers, and this is going to go through now a series of slides which show how the core store and things operate. This is the core store. We've got the modifier, which is part of the accumulator range, an accumulator, some data somewhere in memory, and the functions somewhere in memory, and a variety of registers. Instruction read, you copy the instruction into the X register, which is used as all core store interfaces. Now, those of you not familiar with core stores, and there might be some people who are or not in the audience, reading a core store clears it out. It's a destructive read. So before you do anything else, you've got to write it back again. While writing it back again, we copy the function to a number of other places as well. We copy it to the X register, which is where we have the interface to the core store, and all reads and writes come through there. We've got an operand, which is actually going to hold the operand for accessing the N part of the instruction. Put the X for the X register and the M for the modifier. We also put it all into the N register as well. The reason for that is we might, just might, need to do some arithmetic on it. We don't know yet until we look at the modifier bit. If we've got to modify, we need to take the 14-bit data from somewhere, and it's going to have serial arithmetic done on it. So we need it down here, so we can pick that up bit serially. And being a serial machine, we can just tap into that register and pick out the bits we want. There's the modification read. We read that and it clears it all out. We write it back. And then we've got the serial arithmetic going through the modifier. I can't actually remember whether to take the operand from there or from there. It doesn't matter. You can do it from either. It might be either case, I can't remember. It's 1969, so it's a lot of logic diagrams, it's the code. But once we've done that, we finish up with a modified operand in here, ready to address the core store. So we read the N value now. This is the N part of the instruction, using the operand in here. The function controls what address you're doing. Again, it clears it out. And of course, the next thing you've got to do is to write it back again. And then the next stage is to read the X register. Let's assume we're doing an add. Two instructions, will make sense. Again, the X register modifies the address to select which of the accumulators we're using. And then we go through the arithmetic phase. But, meanwhile, the order number register here, which is the thing that read the order out, we've got to increase that by 1 for the next instruction. That's again a serial operation, so we need 14 bits of shift to be able to do that. So the minimum instruction size is 14 clock cycles. Some instructions like shift, if you only do a place of 1 shift, you've still got to do the 14 cycles to increment the order number register. It's a simple machine. So we write it back. That's the result. And that was the end of the quick gallop through the instruction set. I've produced some tables there showing the actual state. This is modify read, modify write. That will be optional depending on the state of the M register. There's an instruction read and instruction write starting all of these things. So these basically represent the number of call cycles, and there's the instruction times. Most of them are straightforward. All these standard arithmetic ones are 12 microseconds, that's fixed. Shifts vary according to how long the shift is. If it's less than 14 places of shift, it will always take 9.5 microseconds. If it's longer than 14 bits of shift, it will go up to a maximum of 11.75 microseconds. This is one change which I made between the Argus 100 set and the Argus 400 set. The Argus 100 would limit the shift, whatever size you put in there, to 24 places. It's a 24-bit machine. I couldn't see any reason for putting the logic to do the limit there. And there's one function where you can connect the X and Q registers together and shift both. So there is a case where you could actually go up to 31 places of shift. So why not limit it? I negotiated with my managers about this particular thing, and they said, yes, okay. and that was carried forward to the Argus 500 as well. So that's one instruction change that's different. The multiply implements something called the Booth algorithm, which I'm sure there's people here know far more about the mathematics behind it than I did. It basically is, it looks at the bit patterns and will add, subtract, or just shift. I can go through some more detail on that if anyone's interested. And I've got an emulator which can show you later if there's time, or afterwards if you want to stay and have a look. I've got it running on this machine, which will allow you to look at the bit patterns of each case. But basically, if there's a 0, 1, 0, 1, 0, 1 pattern to the end, it will take a maximum of 156. That's the only pattern that takes 156. If you multiply by all zeros, which is the other general case, it's 18 microseconds. So that's the minimum to the maximum. And depending on the bit pattern, it can be anything in between. The divide, I couldn't find any shortcuts for divide. 156 microseconds if there's no final restore, and 162 microseconds if there is a final restore. The Booth algorithm actually caused me quite a lot of grief when I was preparing this talk, because I knew how it worked roughly. But 50 years is a long time to remember, so I did some research on the internet and found it was called the Booth algorithm. I didn't know that until then. So it's only 3 months ago when I started preparing this, I discovered it was called the Booth algorithm. I copied it from the Argus 100, which used the same algorithm, but it didn't use the savings of the time shift. It didn't have this particular saving. It puts it through 24 bits of shift every time. I was adding nothing to something, why bother? I just did a shift. So that's one change I made, which made it considerably faster. Now this is an Argus 100 control panel, and the Argus 400 was more or less the same. I can't remember the details and I couldn't find a picture of it. But basically the panel was fairly extensive. There's things called, I think they're called DM160s, little indicator lights, which indicate in binary what the order number is of the instruction that's being obeyed, the order itself, and the register that's been staticized, and a set of 24 hand keys for interacting with the program. They're used for setting the start address when you want to start the program, or the address where you're reading the primary tape input into it from the tape reader, or the red as an address for my program, so you can actually use them to control the program. There's a button here for read, normal there, read tape, and then start. When you press it down there, it will take the address from there and load it into the order number. Yes, sir?
Was there a loudspeaker?
Don't remember. Was there a loudspeaker? No, I don't think there was a loudspeaker. Sorry, I can't remember. I don't think there was. There's certainly no boot instruction. And this controls, you can actually staticize things by selecting an address on there. It filters these registers so it only shows that particular instruction. So it's useful for debugging. You can also use single step and various things like that for debugging the program. So there was some hardware facility for debugging. And there's another program button here called jump inhibit, which if you go into a loop stop, it's the only way of getting it out of a loop stop. You basically jump inhibit, press, and it will then step over that instruction. Loop stop is the only way of stopping the machine, which is interesting. Loop stops, and the Ferranti machine is fine. At a later company I worked for, if you did a loop stop, the cores overheated and the data dropped out. But the Ferranti machine, loop stop was perfectly okay, no problems whatsoever. The core store, by the way, was designed by Ferranti. The matrix wiring was designed by Ferranti, so the manufacturers were making it to that pattern. We designed the read amplifiers, we designed all the drivers. Just going back to the costs again, when I think about it, the original core store, remember what I said about price of a house? About £3,200 for a house with garage and central heating, new build. That was 1965. This was round about this sort of time. The original core store, I believe, was at £7,000 for 12k words. These were made to order. And how do you make a core store which has got, I think it's 12.5 thou holes in it, and you throw 4 wires through them? Portuguese lace makers is the answer. And they were all done by hand. By having 3 manufacturers and negotiating, they got the price down to £750 for the storage, the production machines. That's still a hell of a lot of money, that's 2 cars. for 12k words. Do bear in mind that, because you can pay back to the costs. The I/O interfaces, process control, you obviously have to have this standard means of reading paper. We use paper tape rather than cards as the primary input. The Argus 100 uses 5-hole tape, the Argus 400 will enter up to 8-hole tape. So we need a paper tape reader, we have a paper tape punch, a console printer, card punch, and we developed a card reader later. Those are all my designs. I finished up being the king of the peripherals, plus a few other things as well. We also needed bulk storage to supplement the course talk. 12k words. This is the maximum we could fit into it. That's 24-bit words. That's 6k bytes. So we had rotating disk storage, and I've got the indentation slightly wrong there. The main disk storage we had was a Burroughs disk. I don't remember the Burroughs single disk. Massive, 1 megabyte. Head per track. The disk itself was about that diameter. The case was from about from here to out where my dick is. It's still about that high, about that wide. Spinning at 1500 RPM. I had a guy from the RAF coming to talk to me about another project. This is to put research equipment into a comet aircraft. He wanted to put one of these in an aeroplane. I asked him, did you want the plane to go up and down or left and right? He hadn't thought about the gyroscopic effect of a disc spinning like that. Take power off, it took 2 hours before it stopped spinning. Yes, I persuaded him to put a tape deck in instead. We chose tape decks. We used an Amtex TR7 tape deck, which is a vacuum column machine, 36 inches per second. And I designed the tape controller for that. I didn't design the disc controller, I did design the tape controller. Interesting with tapes as well is a 10.5-inch spool of tape, a ring of tape, 2,400 feet of tape, and store about 10 to 15 megabytes. Now tape is about the only technology which still exists in a form, but now you can get hundreds of terabytes onto a tape. The difference is you don't have to start and stop it. These were blocks, and with 9-track tape, the inter-record gap between blocks of data, and a block of data would typically be around 2 kilobytes or thereabouts, is 0.6 of an inch. You have to stop the tape and potentially go into reverse in 0.6 of an inch. And you've got to be fairly precise on your timing. So it's quite an engineering feat to design things to run up to 36 inches per second in one direction and reverse in about, I think it's about 10 milliseconds or 6 milliseconds, 7 milliseconds, something like that, I can't remember. It's quite a lot of jiggery pokery to actually get those timings right, because you could reading forwards or reverse direction. So Mac tape was an interesting challenge. These decks were, this was a piano deck, 2 decks mounted vertically, 2 decks mounted side by side. The ones that mounted side by side were about that wide. The spools were side by side that way, so it was a big unit from about here to there. There was one sailing on the QE2, and it was delivered on a Friday afternoon. We had to strip it down, repaint it, and get it to John Brown's shipyard by 9 o'clock Monday morning. We did. They were welding up the side of the ship. It wouldn't go in any other way. But vacuum column machines and process control don't really go that well together with vacuum, because you're sucking air across the vacuum columns. But that was 36 inches per second. Non-return to zero was 800 bits per inch. Later there was phase encoding, which I think came later in my design. We got to 1600 bits per inch. And even later that went to group code recording, which went up to 62625 or some 6620, somewhere about there. 6250.
It was quoted as 6250.
I've never actually did that one. I've done phase encoding, but not that was later. So we need a standardised method of connecting things together. Specialised devices exist in process control. Now, what I've said so far would apply to any commercial process control environment, sorry, any commercial computing environment. Peripherals I've talked about would exist anywhere. But there's not many computers that have analog inputs in their hundreds attached to them. You need to be able to read them in. These were things like measuring boiler temperatures, various other things like that, speed control, tachometers. So we might have hundreds of input devices, input sources. And that's why our I/O address range was so large. We had 10,000 octal, 4,096 I/O addresses available, some of which were pre-allocated, but 4,096 I/O addresses was needed. 1,000 thermocouples, that's a quarter of that space. And that's the big difference between process control and commercial data processing, is the I/O address space. You had analog inputs by bucket load. You could have single-bit inputs, so the control panel. Think of the control panel you see all the things, all of which got switches. They've all got to be read somewhere, and we read all of those in. In some cases, we designed and built the panels for the customer, not all of us. But the A to B converters were quite a large amount of it. They need to be accurate, and we worked to 12-bit resolution. I think the accuracy was pretty close to that as well. That was quite expensive, so it needs to be shared. Now the other thing is, if you want to share A to D converters between lots of analog inputs, you need something to scan around them all. And it's very convenient to the programmer if that happens automatically. So we actually had two formats. You could read them by program, or you could transfer them by DMA. So it just scanned around, and once a second it sampled all of the I/O inputs and fed the numbers into memory. So all the programming you can do is go to memory for that particular value. And of course, that controller is more expensive than. So the scanners we had basically two forms: relays, or we had what was a mechanical scanner, a motor turning round and scanning things around. That was used in Dungeon S, for example, Dungeon S-Bit. You've still got to select a pair of signals. Remember, you're also talking about millivolt signals, because thermocouples don't generate that much in terms of voltage. It's about 150 millivolts or thereabouts. So you can't have something which is going to cause any voltage disturbance to it. Relays were quite good at doing these things. They're rated at 10 to the 8th operation for a dry read relay, and 10 to the 9th operations used in a wet relay, a wetted relay. They lasted 10 times as long. We also had analog outputs, but they tended to be far fewer and very expensive. Each needed their own D to A converters. If I've got time, I'll say a little bit more about those relays in a minute. We've got single-bit outputs, panel switches and single-bit inputs, character displays for displaying the numeric values on the panels, and they were all custom designed. They're not the same as the operator's control panel that I showed you before. These are customized for every individual site. One site, working to 9 in Steele, they had buttons around the plant. In the specification, they said this button had to be capable of being pressed by any implement that the operative had in their hand. And tool of the trade was a 14-pound sledgehammer. And the buttons were around this side. You see the difference between process control and commercial processing. But the interface, standard interface, was called Interface A. It was designed for the 400 and the 500. I only had an input to this design. I wasn't actually the original designer choosing all the pin selections. That was another team. It needs to be able to span multiple racks. A typical I/O system would have 11, 12 or more racks of I/O equipment and one rack for the computer. So again, you see the difference in the range of these things. The density of the racks was all to do with the density of the number of cables you need for I/O equipment. Each thermocouple needs one pair of cables. And you've got 1,000 thermocouples being fed into a rack. That's a hell of a lot of cables. So the cable management actually dictated how we distributed all of these things across these racks. So the 12 rack system was a very large system. Most of them were about 5 or 6. I said already, it needs to be noise immunity to control the I/O equipment. We're trying to make it universal for future range. It certainly was 400 and 500, and the Argus 600 used a subset. It was actually just the peripheral subset. We didn't actually have any analog inputs in that. But it was intended to be used on the Argus 700 as well, but the 700 didn't exist then. It was designed for future computers. The Argus 700 was the first future computer. And some of the I/O devices were still being used when I went back to Ferranti's on the project 6 years later, and they were still using the same card designs that I'd made all those years before. The cabling we used for connecting, again, cost was important. Twisted pair, we found, didn't have such good noise immunity for the sort of environments we were looking at. And initially, I don't know what happened after I left, but we used trickle twist, 2 earth wires and 1 signal. We made the trickle twist cable in-house, long corridors at Ferranti's, standing together 1 corridor with 3 pieces of wire and power drill. Worked very well. But we're talking about quite a lot of, I say a lot, you could probably make enough to cope with 1 machine in a couple of hours that way. And coax would have been better for noise immunity, but a hell of a lot more difficult to manage and terminate. So the triple twist was actually a good compromise. From memory, I think the characteristic impedance was about 150 ohms. I can't actually remember enough of the details about that. These are the signals, and basically you've got the 12 address lines, and the top 4 bits you have both versions available, because it's much easier to actually jump and select which address you want when you do that in our controls. You just choose whether you want the inverse or the standard one, and decode much easier that way. The standard signal 4 bits, you can actually choose which one, take it just into 1 gate, and it all works. These address line showing it's valid. There's signals for controlling the direct store access, as it was called. DMA is called a more modern term. We can address the core store directly. That's only valid if you've got the direct memory access being accepted and it's addressed to the core store. We've got 24 data lines in, 84 lines out. And that's basically what the interface looks like. It was quite easy to design cards to do that. There was 8 interrupt lines, and there were, you can connect more than 1 device to an interrupt line. It was a wired all like interface. So if you wanted an interrupt, you connect several things to the same interrupt line, and it was up to the software to decide which particular device would cause the interrupt. And I think it's called busy lines, which was, I think, a hangover from the August 200 days, where if a paper tape reader was reading, it would set a busy line. But we also encoded that onto the most significant bit of the data, so if the most significant bit was set, it was busy, so it didn't really need to use the busy line. And that's a change that came in with the Argus 400, I think. And there's a couple of switches which show what the panel is actually doing. And there's also an interface lockout which can be set, which stops everything working. These are examples of interface types. Paper tape reader, paper tape punch. ICL, who made our paper tape reader, the TR5B, did the dirty on me at one point. They sent me a letter saying, we're ceasing production of this tape reader in 3 months. It was our primary paper tape reader for everything. We had a 5,000 character second reader, a facet one, which was a lot more expensive. It also had a rather weird characteristic that we were used to using coloured sellotape patching. The facet reader was completely transparent. It's a dielectric reader, not an optical reader. And coloured sellotape was completely transparent to it. However, normal, clear sellotape wasn't. So we had this situation where we wanted to put a patch in clear sellotape using a facet reader. It was also a bit vicious. The 300 characters per second reader would sort of accelerate up, pulling tape out of the trough fairly gently. And as it did, it went straight to 1,000 characters per second. And on one occasion, it took tape out of a trough, just sat here, and it hit the wall at the far side, about as far away as that wall. The tape just jumped into the trough. Started reading, it was all right. The tape was spilled, caught up with it, and then threw the tape across the room. The console printer, the ASR33, was our standard one for the Argus 400. As an aside, I think it was the very first one into the UK. It didn't work when I got it in the line. Called out Westrex, who were the service people for agents, and the guy saying, I'm putting the training course next week. He was a cinematograph engineer. So together with the manual and him, we got it working in 2 days, and I found quite a lot about how ASR33s work. It's actually remarkably simple. We had a line printer, which was the Data Products one. Again, we're talking about cost. We had the drum changed. I believe, and from memory, the fixed price for changing the drums is £4,000. the price of a house. And I had to check that carefully, because I was responsible for getting the character set right. And we produced a card reader and card punch later to do with the match terminal. So the card punch we actually had for the Argus 400 range, but the card reader was only really used as an input for the match terminal. Disk drive, which I've mentioned already. At the time we only had this Burroughs disk. We had the IBM tape drives. And there's a range of some of the things that we actually had as I/O devices. Tracker balls and CRT displays. We had a 1024 by 1024 dot matrix display. Draw graphs on. And the etc's there, I can't remember all of them. It's quite a wide range. Now some lessons that were learned along the way. This is the one that didn't quite make me as hairless as I am now, but it could have been close to it. This was quite early on in my career. There's a guy who's called Ken Johnson. I don't know if anyone knows him. I don't know where he worked, but he kept popping up from time to time. He'd written a program to calculate pi to 500 or more places of decimals. The Argus 100 and 300 produced the same answers. Mine didn't. But it took 5 minutes before it printed any results out at all. So you can imagine that 5 minutes of computing takes rather a difficult task to find out what's causing the problem. I did find it. It took me about 2 weeks of fairly solid work. Remember I said that the multiply produces a 48-bit register, but because of the Booth algorithm, the least significant bit needs to be reset. There was a signal missing from the reset, and it was resetting the 2 to the minus 47th bit in the Q register at some time from something completely unconnected with the multiply function, but it was spuriously being decoded. And it took all that time for it to propagate to significance. That took some finding. And so that was a lesson in persistence. Yes?
Did you hear that pi has recently been counted?
I did, yes.
To 31 trillion places by Google.
Yes, I know. Mine wouldn't go that far. We did 15,000 one time. It took a whole weekend. I think Ken called it that saturated series he was using, and I don't know quite. He calculated E as well. But the analog scanners, which I used to talk about, we had a problem. I was getting reports back. I wasn't responsible for the analog system, but I was basically the chief fault finder for the whole team. We're getting high failure rates being reported back for the relay scanners, scanning boards. The rates of 10 to the 8th operations, they shouldn't have been failing at anything like that. 10 to the 8th operations at once per second is several years of operation. It should have lasted at least 3 years, or even 30 years for the mercury pointing version. Incidentally, the reason for the 2 versions is some plants won't let mercury anywhere near them, depending on what they're processing. So mercury would be the long life variant, but plants that won't accept mercury would try read variant. So I built a rig to actually measure as far as I could, to 24 relays, which is the sample size, and the results were somewhat unexpected. I expected to find a bathtub curve like this, non-sorting failure rate. What I found was that every single relay failed with a very tight margin. From memory, and it's a long time ago when I did this, but it was about 850,000 operations. Every single relay, within the space of about 5%, failed. 100% failure rate. But because I'd run this over a weekend, I wasn't there. So I left it running and discovered, after 1 million operations, or thereabouts, they recovered and went on to end of life. That was 100% of all of the relays from 3 manufacturers. That included mercury-weighted reads as well as dry reads. The failure point was slightly different. Contacted relay manufacturers and said, well, I've never heard of this before. It might explain some problem that the post office is having. I did eventually get 3 sample reads from one of the manufacturers and said, we've no way of testing these, can you test them for us, please? I did, and they were perfect. But our only solution was all the relay boards we put into a rig and ran them for 1 million operations before they went into service. We ran them in. But these are the sorts of problems that I was addressing. This is just two samples of them. That's basically the end of it. That's a reference to something that I picked up, which is a paper, which I think is talking about the Argus 400, and I think it predates the machine being made. I know both of those people, Sid Evans, who uses Sid, name on, and Peter Wolfenholm. I don't know what date it is, and I didn't actually find it until about 3 weeks ago. And it shows a different equivalent circuit for the integrated circuits than I've got, which is why I think it's earlier and predates some of this. But basically that's it, and I did it in the time. If anybody wants to look at the emulator, I think it's probably a bit more sensible if I show this afterwards to a small select group. It's of interest to everyone. That was an emulator which emulates some of the functions.
Thank you very much, John.
Any questions?
How do you want to handle the questions in terms of capturing the question and then the answer? Is that okay?
Yeah.
It'll be okay, fine. So, any questions?
I've got an answer.
Oh, well, that's a good start.
You asked about TTL fan-outs.
Yes.
Regular TTL for regular TTL is 10,
Yes.
and the buffer outputs are 30.
Okay, fine. Yes. I couldn't remember that one. It's all. So
Well,
I
still use it.
okay to shoot. Thank you.
Right, turn it round. We're talking about negative and positive
Yes.
bars and power lines. So we'll go back to questions. Any more? Any questions?
Just another comment.
Yeah.
You're talking about fan-out propagation delays, I should
Yes.
say. You were saying some people didn't bother at all. What I'm saying is, we was to say, if it's 2 or 3, we take the absolute figure.
Yeah.
But if it's 4 or 5,
Yes.
we would derate it slightly.
We
We
wouldn't.
never got a problem with that.
When I went to computer technology, they say don't bother actually doing any analysis, just take nominals. At Ferranti, we said if it will work in worst case, that's fine. If you've got a long chain of gates and it doesn't, then use your common sense. So it was a common sense approach, but we were attempting to do worst case conditions if we could. That was the general policy, but it wasn't an absolute rule. It was just a guideline that you tried to do that. If you gave 2, 3, 4 gates, you would take worst case. It was just the general design principles that I was given when I started.
Any more? Yes?
So what computer have you is on show at team?
There's one in the shelf, there's an Argus 400, which I showed you a very poor picture of. It's when I was last there, which is about a year ago. It was in the case near the Witch computer, in the case. It's mounted on a wooden board. I believe it's probably, because it's mounted on a board and obviously has been, I think, ever since the start, my belief is it's something that was produced as a marketing model to be exhibited or shown rather than a working machine. I don't think it's ever been a working machine. Because remember that the computers themselves are very expensive. I know that the prototype machine was insured for £25,000 when it went to the press release, which was in Sheffield. And the other amusing thing there was that it was insured to be travelling that particular car, and it was icy, and the car went off the road. Somebody else saw the accident, picked it up because it was more important to get the computer to there, and drove it uninsured. But that's what it was insured for, was £25,000. That's just for the CPU and core store.
The car was worth.
New car, I bought a new car at that time for 450 quid.
Yeah.
You mentioned Jodrell Bank.
Yes.
My father had a very great friend called Dudley Sayward,
Yeah.
the group captain, who actually wrote Bernard Lovell's biography and also Bomber Harris's biography. I wonder if that name means anything to you, Dudley Sayward.
No, I don't know that one.
Okay.
I knew 1 or 2 people at Jodrell Bank because they used to come and use some of our computers from time to time. Jodrell Bank had an Argus 100 to control the Mark II telescope. They then later bought an Argus 400 to control the Mark I telescope. Because that was originally analog control. And when I went to Jodrell Bank in the 80s, lo and behold, they had the museum there. I saw the machine because I personally commissioned the first 6, and that was one of them. So I actually saw the machine at commission.
Yes?
I can shed a little bit more light on your choice of Manchester for undergraduate degree. You couldn't do undergraduate computing in Cambridge in the early 1960s. There was a diploma in numerical computation,
Right.
which was given by the then called Maths Lab,
Yes.
then subsequently called Computer Lab, and
Yes.
now the Department of Technology and
Yes.
Basketball.
I knew I knew them quite well later on.
And that was essentially a master's
Yeah.
course, and it was heavily oriented towards numerical computation. Over the years, it became much more.
So I chose the right university.
Indeed, and the Maths Lab was independent of the Maths faculty.
Yes.
It was a freestanding entity like the university library, but only faculties can award degrees, so the Maths faculty
Yes.
processed the computer lab degrees. You could start an undergraduate program in 1968.
Yes.
So amusingly, that was seen as part of natural sciences.
I did know Roger Needham quite well later on, because they had one of Module 1 computers, which,
Indeed.
and I was a fairly frequent visitor to Cambridge.
Yeah, two in the computer lab at that
Yeah.
point. So I passed off the cross, but I was there 75 to about 85.
Possibly. I knew the two Robins, Fairbairn and Walker, quite well.
I guess that was overlap somewhat.
Yes. But that was a later career. This is just the first years of my life.
Of course, you couldn't do Cambridge engineering with being an electrical engineer, and that's still true. You just have to sign up as an engineer.
Yes, please.
Given these are process control machines, what sort of language do you use to use the program?
Ah, right. Initially, they were all assembler. The assemblers were fairly primitive to start with. It's actually called initial orders, where basically the first version of initial orders, you reverse the instruction set, so it was accumulator, order, modifier, and address. And the address you could make symbolic. Those bits of numbers. You could have any number, any you like, but it was V1, V2, V3 for the variables. And you could only do, in initial version, initial orders version 1, you could only do backward references. By the time you got to initial orders version 3, you could do forward and backward references. They then produced something called Astral, which allowed you to use symbolic instruction names. But it was still the same sort of thing. So that was basically the primary language that was used. Somebody also produced a Fortran compiler, the machine, which that was quite fun in the way in which it worked. It used a two-pass device. Basically, you put the Fortran program in, it parsed it, and output things from the punch. The output stuff in the punch effectively in reverse order. So you took the output from the punch and fed it straight into the reader, and it read effectively the tape backwards. So you didn't have to rewind the tape. Tear it up and rewind it. It took the last bit of the punch, you took it up and put it into the reader. Not the first bit, the last bit. So it read the tape backwards. I don't know if it may have been, but there were all sorts of other people producing languages. There was also an Atlas Autocode version written for the Argus, and that's the one and only programming course I've ever been on. I have a half-day course on Atlas Autocode. The Fortran was actually very efficient. The Fortran compiler writer put a challenge saying, I've written this program, I've got this subset which is compiled, can anyone beat it with assembler code? The Fortran compiler beat 30 programmers in generating code. There was one instruction less. But we did have an Atlas Autocode, but again I don't think it was used very much. I was basically an engineer and I was writing test programs, so I tended to write all of mine in either initial orders or Astral.
John, I'm not sure if I understood you correctly, but you were, I think, suggesting that in order to deal with a large number of analog inputs,
Yes.
you would actually cycle round.
Correct. Yes.
Is it a mechanical cycle or a logical cycle?
It was basically a logical sequence selecting each relay in turn, which switched the analog input into the D to A converter, sorry, the A to D converter, which then was direct memory accessed and written into memory.
Right.
It then selected the next one.
I asked the question because when I first arrived at ICL, what I had known as a communications multiplexer, I referred to this thing as 7090, no, it's not 7090, 7030 or something, 7930. I referred to this thing as a multiplexer and I was told off this was a scanner. And a scanner differed from a multiplexer because a multiplexer had actually got a circular mechanical system for picking up different inputs from different places.
I wouldn't make that distinction.
Whereas a scanner used an electronic system for selecting which input it was dealing with at any given time.
Strange definition.
Something is a very strange.
We had a mechanical device which was used in the Dungeness power station, which was basically an electric motor driving a commutator round
Yes.
with brushes on it,
Yeah.
and that was called a scanner.
It was the other way around.
That sounded like a good idea because it was gold plates, but the problem was the plastic smeared over the gold plates and had to take it off and skin the surface every so often. So nothing perfect, yes, Tim.
The instruction set layout seems sort of vaguely reminiscent of the 1900s.
Well, I think we probably got a common ancestor.
Yes.
The 1900, as far as I know, was developed independently of this. I know that there was a lot of borrowing from the Pegasus stage, and I suspect the 1900 may well have had the same ancestor when you look at the layout. I don't know enough about the ICL or ICT side to know that was the case. But the Argus computer was developed in about 1958, I think. So that was when the ancestry started, and the Argus 100 was developed from the Argus 200 computer, rather than any other common ancestor. 1900 came later, I believe.
I can say that the 1900 derived from the FB 6000, which was done in Canada.
Yes, I know of that one as well.
Yeah.
So there isn't really any relationship with this then at all?
Yes, common ancestor.
There's a common ancestor somewhere along the line.
Yes.
The FB6000.
Is there a question to that?
Yeah, the FB6000 was Ferranti Canada,
Yes.
but they were working on logic boards produced at West, using logic packages produced at West School for the Orion 2, which was a follow-up to the Orion 1 and follow-up to Pegasus, so there was a sort of common ancestor line through that.
Yes. The other interesting thing is Ferranti's had another computer division based in Bracknell, which produced a Hermes range of computers. And there was intense rivalry between Wythenshawe and Bracknell. And I don't want to say too much for fear of libel. The only thing I can comment was that in 1964 I was sent down to London as the engineering. Remember, I was only 21 and I've been working for Ferranti a year at this stage, as the engineer in charge of the exhibition computer and to answer all technical questions that came along at the IE exhibition. And Hermes computer was just round to the left. The stand managed to tour me off a strip for not getting there soon enough on the Sunday afternoon. Well, the Hermes people have been working there since Saturday morning and still not got it working. They got theirs working about noon on the Monday after the exhibition opened at 9. I left the exhibition half an hour after I got there. And it wasn't working. He did apologise afterwards, but he told me off a strip on the day. How to intimidate a 21-year-old engineer?
Just an observation. I'm not sure those of you in the CCS who remember as far back as the tote machine, but that actually had a mechanical scanning system which picked up the bets from the individual betting stations and fed them into the mechanical accumulators. And you sort of sat there underneath that enormous scoreboard that every dog track had, with all these things whirring round and ticking away and relays and everything. That struck me as being a sort of real analog computer. None of it's electrical nonsense, electronic nonsense rather.
They did actually come out twice for quotations for computerising that. I quoted for them twice.
Yeah.
Certainly once at Ferranti and I think once at Computer Technology.
Yes. One of the people who studied tote machines actually had never seen a real mechanical tote working. He spent his entire career replacing them with electronic machines and just seeing them go out in the scrap wagon.
Yes.
This is a marketing question, right?
Yes.
Really. When you were involved in battery development, what did you see or what did you see as your main competition systems elsewhere? There's a particular reason I asked this question, which I'll reveal, because I was in parallel with you at Elliott Automation.
That's I believe was our main thing. I think Simon knows more about
900 series, etc., which seem to have a lot of similarity, and
yes,
we're addressing the same.
I believe that Elliott's were our major competitors on whichever way around you take it. We were both heavily involved.
Yeah.
Ferranti's, I don't know quite how you'd rate their success with Elliott's.
Ours didn't fall to bits in the shape.
That was only the military version, actually, to the British.
Well, one I've got at home doing Nimrod, so it's...
Yes. Well, he didn't have to fix the problem.
Okay. Well, fascinating. Thank you. And stimulating and interesting discussion. There's great things about these meetings. That all these extra nuggets come out and stimulated though by the presentation and the speaker. Thank you very much.